Welcome. This is 49J3 and this is analyzing simple circuits. And I have to say immediately that the term simple circuits is a little bit misleading. Later on in the course we'll do a more complicated circuit using a thing called Kirchhoff's rules, and because it's formulaic, because it tends to follow the same pattern, the success rate on that system is really quite high. And with simple circuits, there are so many ways you can approach simple circuits, and there's often many steps to approaching the simple circuits that often a new student it will take quite a while for them to get the same level of proficiency with simple circuits that they would do with a Kirchhoff circuit. So don't think because it says simple circuits that it's going to be just a piece of cake. It's actually a bit more challenging. So here's the kind of setup we have. Imagine a circuit. We have some kind of power supply, and then we have a couple of resistors in series with a parallel combination. That could be an example. It could be a series within a parallel combination, etc. This is a parallel within a series, and we could have a series within a parallel. We say the entire circuits and sections of a circuit obey Ohm's law, delta V equals IR. That's very useful. The potential difference need not be the same across different resistors in a series section, but the sum of the potential differences equals the potential difference across the entire section. So what that's saying is, if I have 3 in series, I can basically turn around and say these need not be the same, but their summation equals the EMF that's been applied, for example. Then we can say the current through a series resistors is the same for all, and that's true. Whatever current goes through the first resistor goes through the second, goes through the third. And then we say the current need not be the same through different resistors in a parallel section, but the total current within the section equals the current that enters and the current that leaves. So if I have, say, a power supply, and then I have resistor, 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 the current flow here might not be the same as the current through there or the current through there, but the sum of these will equal the current coming out of the battery, or at least the current entering the parallel branches. And then the next thing we can say is the potential difference across the parallel resistors is the same for all. So the potential difference across this is the same as the potential difference across that is the same as the potential difference across that. And at the speed that we're going, you might be turning around and saying why, and the answer is there's good conceptual reasons for that, and it's worthwhile doing a bit more digging in something like that. Hopefully you're introduced to this in a more fundamental physics class, but if not, then it's worthwhile getting a more basic textbook and going back and just getting comfortable with series and parallel. 12 volt EMF is applied across a resistor network. What is the current flow through the 2 ohm resistor? So let's just highlight this. I want to know the current flowing through that component there. And I'm going to do the slow and steady way of doing this. Well, try and solve it in one step. I'm going to use Ohm's law. I'm going to say, well, delta V across the 2 ohm resistor is equal the current flow through the 2 ohm resistor times the resistance of the 2 ohm resistor. Can you see my nomenclature there? So I say my current flow through the 2 ohm resistor is equal to delta V across the 2 ohm resistor divided by the resistance of the 2 ohm resistor. So I2 is equal to delta V2 over 2, because I know the value of that 2. But I don't know the value of delta V2. I don't know the voltage across it. So I can turn around and say, oh, hold on. My EMF, that's the 12 volts, is equal to my voltage across the 2 plus the voltage, whoops-a-daisy, delta V across the 6. I'm basically saying this voltage here plus that voltage there equals that voltage there. Well, why not the 4 ohm resistor? And the best analogy I can use is if you have a house which is a 3-story house. You have one staircase which goes from the ground floor to the first floor, or if you're in America, it's the first floor to the second floor. And then you have another pair of staircases that go from the first floor to the second floor, or if you're in America, from the second floor to the third floor. And it doesn't matter which staircase you use to get from this level here to that level there. You could do the 4, you could do the 2. They change the height by the same amount. Well, the voltage drop at the top of the 2 is the same as the voltage at the top of the 2 is the same as the voltage at the top of the 4. And the voltage at the bottom of the 2 is the same as the voltage at the bottom of the 4. So I don't need to take them both into account. So I'm going to clean this up just so that we have this. So we have this. And, well, I can rearrange it and say, well, the voltage drop across the 2 is equal to my EMF, which is 12 minus my voltage drop across the 6. Now I want to know the voltage drop across the 6. And so I can say, well, you know, my voltage drop across the 6 is equal to the current flowing through the 6 times the resistance of the 6. So my voltage drop across the 6 is equal to the current flowing through the 6 times 6. Oh man, if I only knew the current flowing through the 6. And you say, well, my current flowing through the 6 is equal to the current flowing, and I'm going to say around the circuit. Let's do I circuit, which means I circuit. And what we see is the current flowing out of the 6 is the same as is flowing round the rest. Okay? Then I say, oh, but the voltage of the circuit, which equals my EMF, by the way, this guy, is equal to V equals IR, the current flowing around the circuit times the resistance of the circuit. The resistance of the circuit is all of this. So I say, oh, I'm going to combine these using my methods of networking resistors. And I recognize this is a parallel bit that's in a series combination. So I'm going to say, oh, 1 over Rp is equal to 1 over R4 plus 1 over R2, which equals 1 over 4 plus 1 over 2, which equals 1 over 4 plus 2 over 4, which equals 3 over 4. And of course, because I've been practicing, I know that Rp is equal to 4 over 3. Remember, you've got to flip it back. Very common mistake not to flip it back. This is ohms. So now I can draw my circuit as 4 over 3 and 6. And that gives me R series is equal to R1 plus R2, which equals 6 plus 1.33 is going to be 7.33 ohms. Now, I've actually made some progress because I know the total resistance. So over here I can say that I circ is equal to EMF over R circ, which equals 12 as my EMF over 7.33, which equals, and I like to work out the numbers, so 12 divided by 7.33, let's clear this properly, 12 divided by 7.33, and that's going to be 1.64, and this is amps. And so I know that my I6 is 1.64 amps. And so I know that this is going to be 1.64 multiplied by 6. So that's going to be 9.82 volts. And so this tells me that my delta V2 is 12 minus 9.8. So 12 minus second answer is equal to 2.18. So this is equal to 2.18 volts. And I know that this equals, well, it's going to be 2.18 divided by 2, which is 1.09 amps. 1.09 amps. Can you see how I used Ohm's law and then something else and then Ohm's law and then something else and then Ohm's law, and the something else tended to be conceptual? That's the pattern. And the other pattern is we tended to go from talking about a specific component, working our way out until we were talking about the entire circuit. So this is not trivial. The equations are easy, but it's not trivial. Finding your way through it is not trivial. Now, is that the only way to do this problem? And the answer is no. There's other ways of approaching it. For example, I could turn around and say, you know, if I can find my I circulating in the circuit, then I know that that current divides into, well, some of it goes through the 4 ohms and some of it goes through the 2 ohms. Let's call that 6 bits. I can divide that current into 6 bits, and then I can say that 4/6 of that current goes through the 2 because it's a low resistance, and 2/6 of that current goes through the 4 because it's a high resistance. And so you find people, once they've been around these circuits for a while, they start using ratios, and they can almost intuit their way through circuits quite readily. Whereas when you first begin, it's kind of like you've got to just feel your way. Let's look at another example. This is another example where this is a series part that's in a parallel combination. Okay, so what we want to do here is we want to find the current flow through the 2 ohm resistor again, but now the 2 ohm resistor is in a very different environment. And well, again, there's many ways of doing this. It seems to me actually that probably the easiest way is you say, well, if I can find the current flowing, if I can find the current flowing through the whole circuit, and then I can subtract from that the current flowing through the 4 ohm resistor, I'll be left with the current flowing through the 2 ohm resistor. And so I say I circuit is equal to delta V circuit over R circuit, which equals 12 over R circuit. And my R circuit is going to be, well, let's look at this. We have a 4 and we have a 6 and a 2. 6, sorry, get this the right way around, 2 and 6. So these are in series, so I say R series is equal to R1 plus R2, which equals 2 plus 6, which equals 8. So I get 4 and 8. And I say 1 over R parallel is equal to 1 over R1 plus 1 over R2, which equals 1 over 4 plus 1 over 8, which equals 3 over 8. So R parallel is equal to 8 over 3, which equals 2.67 ohms. And then I say, well, okay. Then going back up here, I can say, oh, this is 12 over 2.67. So my current leaving the battery is going to be 12 divided by 2.67, which is going to equal 4.49. So this equals 4.49 amps. Basically 4.5 amps comes out of here. Out of, let's imagine my pen gone. Sometimes I can't see my pen, so comes to here, and then it splits. Now I can easily find out the current through the 4 is equal to the potential difference across the 4 divided by the resistance of the 4. And I know my potential difference across the 4 is 12 because there's no potential difference in the wires. So this here is 12 volts above that point there. So that's going to be 12 volts. And I know that my resistance of the 4 is 4 ohms, so that leaves 3 amps. So if I know 3 amps is going down there, and I know 4.49 amps is flowing through there, then that means that I2 must equal 4.49, the current in the circuit. Let's write it down as an equation. I circ minus I4. So I say I2 is equal to 4.49 minus 3. I2 is equal to 1.49 amps. All the math is easy, but it's like eating spaghetti. It's like you know how to do it, but doing it, quickly and elegantly takes practice. So there we have it.